Let's go through LeetCode 1778, shortest path in a hidden grid. So it's given hidden grid in there is a robot, and you say that you are trying to uh, s- uh, getting from the target start from a start cell and goes to the target cell, and the grid is with size m multiplied by n, and each cell in the grid is either empty or blocked. It's guaranteed that the starting cell and the target cell are different, and neither of them is blocked. So starting cell and the target cell is not blocked, and you want to find the minimal distance to the target cell. But the thing is that you don't know the grid's dimension in the starting cell or nor the target cell. And then you are only allowed to ask the query to the grid master object. And then this grid master class, you'll see it has three methods. One is Boolean can move, and which can have a chart direction and void move, and also an Boolean is target can check whether this cell is a target or not. So let's see the direction. This chart can only be up, down, left, right. And retain the minimal distance between the robot's initial start cell and the target cell. If there is no valid path between the cell, return -1. So here the grid is not given, but we are given a grid master. So what we do this question is that we should use this grid to do a DFS search to try to see if we are able to use the can move or is target, trying to see if we are able to to uh, go from the start cell to the end cell. And by doing the DFS search, the problem is that we cannot use the DFS to trying to get all of the paths and then do the trying to comparing the smallest, because to get all of the paths, the recursive depth can be very deep. So but the thing is that it is possible we do DFS and find all of the cells whether they are able to visit or not in some limited iterations. So the concept is that we do DFS first from let's say the start, the board, let's say the start is initially at because the start in the target is not known. We don't know the coordinator. We actually we can say the start is at the original point, and we do DFS to do search all of the cells around, trying to see in some kind of limitations. For example, limitation is the n is n and m is smaller or equal to 500. So we can search, for example, grid like from 1000 multiple by 1000 grid. has the limitations. And let the original, we can point as that 500 and 500 and do search this kind of grid. So for the DFS, what we do is that we try to DFS from this kind of original set, trying to see all around whether it's possible that the neighbor cells are able to visit or not. And in this case, we do DFS because we have the bound, right? That is from 0, 0 to 1000, 1000. So if we visit all of the cell, it doesn't need to recursive call all of the paths. It just needs to visit all of the cells, right? So I say that if we have n and n cells visited, so those kind of DFS time complexity will also be ON. So after we do DFS, right, we should be able to see if this robot is able to retrieve the target or not, right? Also, we find all of the cells in this kind of hidden grid that whether it is obstacles or empty cell. So by doing this, then what we do is that we do another BFS from the origins. Origin is the 500 and 500, the start, right? But then BFS to see to do the target, right? To find the shortest path. Why we cannot do BFS only, right? Because BFS for every layer, originally it goes to many layers, right? And for this robot, you cannot jump from one cell to another without go back to the origin, right? Because the grid master can only move continuously, right? So we can use the grid master to do the BFS, DFS, right? But for BFS, because the cell we are already given, then what we do is that we don't need to use a grid master to do BFS. We can just from the original, right? And to do BFS find the shortest path. And this will be proven to be true because if we BFS find from this to target, it's 5 steps, right? So for us, let the grid to go is just this kind of BFS path should be good enough. But when we do BFS, we don't use this grid master to do BFS again because we cannot move a cell to be another which is not connected cell, right? But if we find the shortest path, every parent to its child is connected, right? So the path will be the shortest path. So let's write code for this. For this one, we are going to have, for every, we need to have the direction array, right? So we should have final static int 0 equals, and so for this grid, we'll see it can only move passing the character, right? So we should have the direction as character as another array, right? Char array, which called dir, right? So the row move down and the column doesn't move. That the first one is a D, and this will be an right. And the third one is an up, and the last one is an the column is moving left, right? So what be so we'll see. It has a same we should those kind of four index. Um, we have the DRR with its related directions. So what we do is that we are going to create a board, right? Because we'll see this board is has a limitation of 500 and n and m is smaller equal to 500. So what we do is that we can have a border equals new int 1000 multiplied by 1000, right? Because initially we set up 500 and 500, and this will be enough. So you'll see this grid is either minus 1, 0, 1, or 2, right? So minus 1 means minus 1 means this is a start point, and 0 means this is blocked. 1 is empty, 2 is target, right? So we can initially set, for example, set a value to be minus 2. Because 0 means that is blocked, right? So we should using the DFS to fill the data, or otherwise you can use a capital integer, which means initially it is none, right? Then we'll have border 500 and 500. That is the start point equals minus 1, right? The starting point. Then we'll have a Boolean in reach equals DFS. So DFS, we're going to have an return value, whether it is reachable, the target is reachable or not. So board master 500, that is the current row, current column, and we are going to have a weight for new hash set. Um, um, we can use integer, right? Just have row current row multiplied by 1000 um plus the column, right? Cavity. So return can reach. So if we can reach, then we're going to do BFS just to find the shortest path forward, and from 500 to 500. Um, and because we already during the DFS we set the target to be 2, right? So of course for this DFS you can return a cell which is target uh and check if the target is not or not, right? But for this one we already marked this as 2, so we just return Boolean should be fine. Otherwise we just return minus 1 means we cannot reach. So the first one is that we're going to do private Boolean, do a DFS, right? So this will be our board. And we need to pass in the grid master, because in DFS is moving consecutively. And we need to pass in this grid master instance in the current row and the current column. And we are going to hash that integer for the related, right? So this was the DFS. So every time we DFS our exit condition is that our master, if this is target, if we check if this is target, then board row column we mark as this one as true, and we return true. And we're going to have key, right, equals row multiply 1000 plus column. Let's make sure the row and the column, this range should be in enough, right? So let's say if validity 的 contains key contains this, that's called or then we're going to return false, right? So then we're going to have validity 的 add this key. So so then what we do is that we are going to for int k equals 0, k smaller than 4, right? K plus plus. So we know that int new row equals row plus d row k. Int new column equals column plus d column k. So of course we can check the boundary if new row is greater equal to 1000 or new row is smaller than 0 or new column is greater equal to 1000 or new column is smaller than 0. We should continue, right? And we need to check whether our current cell is able to move to the new row or new column, right? The new cell. So we need to use the master can move method to check, right? So if master can move, so this is passing the direction, right? So for every k index, if this kind of new cell, we just move to the use this kind of new dir, right? So can move dir k, right? Then what we do is that we're going to have board new row new column. So means this is empty. Empty is let's first set this one as empty, right? The empty is 1, right? But since it's that we set this one as empty, um, and we should have this one to move dir index, right? And for then what we do is that we need to DFS to the new row, new column. But if this one, for example, this new row and new column is target, right? So it will be set as true. So what we do is that then we are going to have let's have a find variable called Boolean find, so that find equals false. And we'll say this found should found should all equal to, right? DFS for master, new row, new column, innovative. And we should do backtracking, right? So for backtracking, that is for move down, then we should goes to up. If it is up, then that will go down, right? If it is left, then right, then go to left. If left, that will be right. So what we do is that our DRR should +2 mod 4, right? So that is moving back. So that is to for this this grid master, how can we do backtracking is move dir should be this index +2 mod 4. So this is backtracking. And if we cannot move, right? So what we do is that we just set this for uh, new row, new column equals 0, means this is blocked. And in the end, we return found, right? So by doing DFS, we put our this kind of board, whether it is put the cells which is empty or blocked. Also, we do this. We can see if the target is achievable or not. And then we write a BFS, right? BFS, we don't need to pass in the grid. We just um, use because we already have this board. We mark as 0 or 1 or 2, right? So for BFS, we just use this grid. This board, we already filled the number to find the shortest path. And for this short path, it's guaranteed because for BFS, every parent and its child is just one step, right? So that if we BFS find how many steps, so that will be our result, how many steps. So what we do is that we're going to have private int BFS. So we're going to have a board we already marked and have a starter row and starter column, right? We don't need to have a target row or target column because it's already been marked as true for us. Right. So what we do is that we're going to have a queue int q equals new array stack. Then we're going to have set integer visited equals new hash set. And we're going to have Q offer of course, if you don't pass this variable, it still be fine. 500 passing new int starter row starter column, right? And we are going to have a related add 500 multiplied by this one plus 500, right? Yeah, sorry, use this because we but it is as actually 500, right? So what we do is that we're going to find the results, the minimal steps. So what we do is that while this kind of queue is not empty, then minimal step we need to have a layer. So size equals to q dot to size Then what it is that for in I equals to 0, I smaller than size plus plus. So what you do is set result to the plus plus, right? So we'll get a current cell into current equals Q dot pool, right? So that means if this kind of board current cell, right? Current equals to already, then we just return results. Then for BFS is we have four directions for input k equals to 0, k smaller than 4, k plus plus. Then we're going to have into new row equals current 0 plus e row k, right? And into new column equals current column plus d column k. And also we need to check the boundary, right? So we'll see into the new key, right? So whatever equals new row multiplied by 1000 plus new column. So what we do is that if new row is greater equal to 1000 or new row smaller than 0 or new column is greater equal to 1000 or new column is smaller than 0 or uh, or variable that contains key, right? Or this board board new column is smaller equal to 0 means um actually that is we will mark this as -2, right? That means some of DFS is possible. It just give you the achievable sales, right? But it's possible. For example, there is a um, zero block here, right? Block here. But there is still -2 somewhere, right? So we will also add this one. If this is smaller or equal to 0, we just continue. And then we are going to have a related add key, right? And Q offer new int, new row, new column. So, and in the end, we should return results. So this will be the code. So we do DFS first, then do BFS. Variable star column 31 is already length 31 is already defined. This should be start column. $31. This is not the index, it should be k, right? We have k. So this will be pretty much the code. Um, we also need a Python version. So the Python version is very similar. We can have, for example, also have the D row, D column, and the DIR equals. So this one will be 1 0, minus 1 0, and this one will be 0 1 0 minus 1, right? So for DIR, the direction will be mm, D R U L, right? Um, so we need to define BFS and DFS. Um, so for for uh, for the DFS, we do um, we can put this one in the solution, right? Because we may need to use uh, so we are going to have board equals set as -2 multiplied by 1000 or in range 1000, and we'll say can define the DFS as row column weighted, right? Weighted. Mm, so this one will return Boolean. So let's say, and this DFS is if um, we have the master is target, then we're going to have for the row column equals true, and the return true, and then um, for this key and for Python, we can just have a pair, right? So we can have key equals row column. We don't need to, we can convert this as the integer multiplied by 1000. So we'll see, for Java, we convert, but for Python, we can just has this kind of tuple, right? So we'll say if p invalid, return false. And I will say, mm, and then what we do is that we should add this key, right? And we can have a found variable equals false. So we're going to have for k in range 4, right? We're going to have a row, new column equals row plus d should have self dot d row k. Then the new column will be column plus self dot d colon k, right? So let's check the range. If not 0 smaller equal to new row smaller than 1000, uh, um, if not and 0 smaller equal to new column smaller than 1000, right? Then we should continue. Then we'll say if master dot can move to the to this new row in the new column, right? Then we're going to have a for the new row, new column equals 1, right? And then we have master move self the dir k, right? Uh, and we'll have found all equal to dfs new row, new column related. And then we backtrack that is master move move self that dir a plus 2 mod 4, right? This is backtrack. Else we just set this kind of border, new row, new column as blocks, right? And return font. So this is DFS. And also we should define the BFS function, right? DF BFS. So start row, start column, and actually this is 500, right? From let's have a deck. Let's say from collections import. Okay, right. So we are going to have Q equals deck. We should add a row column, and we need to have weighted equals stat, and then we are going to have weighted add this row column top stats equals to 0. So while Q is not empty, then for this one in range length of Q, we're going to have x, y equals to Q dot top left, top left. So let's say if for the x, y equals to, right? We just return steps. Then we should for the 4 directions for k in range 4. We are going to have a new x, new y equals x plus itself at d 0 k, and the new y will be y plus self at d column k, right? So if not 0 smaller equal to new x smaller than 1000, and 0 smaller equal to new y and smaller than 1000. should I continue? Um, let's say if nx ny in weighted forward new new nx new ny is small equal to 0, and we're going to continue, right? And then we're going to have weighted at this tuple new x new y, and we'll have q append this new x new y. And for this kind of every layer, we should have steps that class equal to 1. And for this BFS, when we jumping out of the while loop returns -1, right? So for our main function, what we do is that to return um, return BFS 500 500, right? If DFS if DFS, so what are we passing DFS? 500 500 else that is -1, right? Mm. One, two, unpack. We have egg. Mm. We should add this. So, right? So if we have a DFS weighted endpoints, right? And then we do a BFS, both so we'll say if we weighted endpoints on this kind of board, then BFS that is also a linear operation, right? So time complexity will be ON and space, right? That we are using also the linear data structure. So that will also be ON.